All right, welcome everybody to this week's GOCC. We're very happy to have Mojde Feller, who is going to be telling us about covers and chains in Katalan Combinatorics. Before we start the talk, I just want to remind everyone of our community statement, which says that 1, we are all learning, 2, everyone has something to contribute, and 3, no one has all the answers. Okay, without further ado, Mojde, take it away.
Thank you so much for the introduction, and thank you so much for letting me speak here. So as Sarah said, I'm going to be speaking today about Katalan combinatorics, or I might say Katalan combinatorics in one point, as well as covers and chains and how they arise over there. So I'll tell you what all of those words mean in a second. But before I talk too much about those covers and chains, let's talk a little bit about Katalan functions. So Katalan functions, when I say that, I'm really just talking about K-theoretic Katalan functions. So what are those? I would like to maybe just peel away the layers here and first say that they're a K-theoretic extension of the Katalan functions. So simpler question, what are those? Well, the Katalan functions were introduced, I believe, in 2010 independently by several different researchers. And then they were studied quite a lot more in 2018 by Blasiak, Morse, Pun, and Schilling. Sorry, not Schilling, Summers. While in 2010, Chen and Panyushev had introduced them. And the Katalan functions were studied because of their relationship to K-share functions in part, as well because of their relationship to the Euler characteristic of vector bundles, but I'm not really going to dive into any of that stuff. I just wanted to say that if you're familiar with the Katalan functions, what we're looking at is like a K-theoretic extension of that story. So what else can I say about them that is maybe a little bit less lofty? Well, for one thing, these are functions that specialize to symmetric functions that we might know and love a little bit better. So when I say that they specialize, what I mean is the K-theoretic Katalan functions, which I'll define explicitly in a moment, we plug in certain parameters to define them. And by picking special versions of those parameters, we can get back symmetric functions that have been studied quite a lot. So what that means is that when we understand more structure of the K-theoretic Katalans, maybe we can also get back some info about symmetric functions we're already curious about. Okay, the next thing I'll tell you about these guys is that every K-theoretic Katalan, or every Katalan, as I call them, is represented with a picture like this. We're going to talk a lot more about these pictures later today, but for now, I'll just say that a picture like this, wherein we have a grid with numbers across the diagonal, certain red squares, and certain black dots, this completely determines a certain Katalan function. On the other hand, given some Katalan function, I can immediately write down a picture like this. And so for our purposes, often we'll instead work with just pictures like this, talk about the combinatorics of these kinds of pictures, and that's equivalent to getting information about the Katalans. So later I'll tell you how these red boxes are chosen and how the dots are chosen and so forth. But I just wanted to explain that there's some important combinatorics behind the scenes here. And the last thing I'll say about them before we dive into the specifics of definitions is that these guys are used to define a certain family of functions called the closed K-share Katalan functions, which I study quite a lot. And they are a basis for symmetric functions that have been conjectured to have a relationship with the quantum growth and Dieck polynomials. And that's where the covers and chains in today's talk title are going to show up. So we're going to talk more about those specific functions later today, but I basically wanted to say that the Katalans became important to me specifically because of their relationship with this family of functions. Okay, so before I can tell you how to write down the definition of the Katalans, we have to build up a little bit of machinery. So let's do a little bit of notation and definition work. The first symbol I'll use a little bit today is delta plus L. And for the rest of this talk, I'm always going to fix some L and some lowercase k. Those will just be two fixed positive integers. Okay, and so fixing this L, delta plus L is just a series of ordered pairs ij, where they lie between 1 and L and I is smaller than J. And we'll see an example of this in a second that'll make this a bit easier. I'll also talk about root ideals. So root ideal psi is basically a subset of delta plus L. So it's a subset of those ordered pairs, and it has a certain partial ordering given on it. If you're not familiar with this concept, don't worry about it too much. I'm going to tell you maybe an easier way to understand root ideals for our purposes in a moment, and it'll be easier to understand with a picture. I'll also use the letter M to denote a multiset. So a multiset, it'll just be like a set with repetition. So let's do an example. So if we take delta 5 plus, I could take psi as this, this set here. You can check that it satisfies the definition. That's just one example of a root ideal in delta 5 plus. And M, I'm going to take as an example 2, 3, 4, 4, 5, 5. And here's how I would represent that information with pictures. So when I have red boxes on a grid, that is a root ideal. That is representing a root ideal. And the root ideal in this example is shown on our grid. So when you see a grid, the way you'll think about it is that the first row gives us like the first argument here. So this box where my mouse is 1, 1, then we have 1, 2, and so forth. On the other hand, the columns of this grid, that tells us the second argument. So right, here we have 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, and 3, 5 represented. And maybe the easier way to understand root ideals that I was kind of referencing is that they come from Dick paths. So if you were to start right over here where my mouse is, and you were to end over here, and we're not allowed, and we're going to get from there to there just using steps like I'm taking here. So I'm making horizontal and vertical steps. And I'm not going to allow myself to go past this diagonal here. So I'm just taking Dick paths. They're like Katalan number, many of them. Each of those gives us a root ideal. So with this example, the path is like that. Okay. Now let me show you how we represent the multiset. So the multiset, any multiset we take will be represented with dots on a grid. And all of these grids, by the way, will be 5 by 5 if we've picked L as 5. And what we're doing is we'll just put dots that are kind of justified all the way to the top of the box, the top of the grid if possible. All of the multi-set numbers are telling us what columns to put things in. So we have 1 dot in column 2, 1 dot in column 3, but we have 2 dots in column 4 because 4 shows up twice in this multi-set. Okay, so that's how we represent our multi-sets. And the final part of this example is that I wanted to say sometimes we talk about delta 5 plus without our root ideal. So the delta L plus in general, pictorially, would be every box sitting strictly above the main diagonal, so like northeast. And then if we were to say what's delta 5 plus without psi, in this case, it's these 3 yellow boxes. Okay, so kind of a lot of machinery, but that's what we're going to use in a second to work with our Katalans. Okay, so given that, we can finally write down maybe our first definition of what a Katalan really is. And so a Katalan is defined over the 3 parameters I was referring to. The first one is a root ideal psi. The second one is a multiset M. And lastly, we take gamma to be a list of L integers. And so you'll notice I'm not requiring gamma here to be a partition, which is usually how we talk about symmetric functions. But for right now, let's just take gamma to be kind of any weight. That's what word I'll use to refer to this third argument. And once we've picked those three, we define our Katalan function using lowering operators and raising operators. So a raising operator, Rij, what it does to a symmetric function is that it takes its subscripts and it increases one of them by 1. It increases the ith part by 1, and it's going to decrease the jth part by 1. And the lowering operator does something very similar. It just it doesn't raise at all. It only lowers. It just decreases the jth part by 1. Okay. And this G gamma, I'm not going to define it, but it's just some function. So we have this like ugly definition we can work with, and the raising and lowering ideals, they're a little bit informal. So if we actually wanted to work more with this definition, we would have to formalize a little bit there, but let's just kind of take that for what it is. And these were, this definition was introduced by Blasiak, Morse, and Seelinger, but shortly afterwards, they provided this second proposition of like a way to define them slightly differently. We're still going to have a multiset, but instead of using our psi to index the raising operator, we will use delta plus L without psi. I'm missing the L subscript here because, like abusive notation, it's sort of just understood that if we have our L fixed, delta plus is the same thing as delta plus L. And this K gamma is just another function that is also ugly to define. But so maybe you'll trust me that instead of writing down this mess, it's easier to just pictorially show our psi m and gamma with the boxes and dots and grid. And that's the world we're going to work in for the rest of the talk. I'm not going to talk anymore about raising and lowering operators. And so this is like an example of one of those depictions. I've taken psi to be this root ideal. M is as before from the previous example. And then I'm just taking gamma to be 3, 4, 4, 2, 1. And this is how you would draw that. This is how you would draw that picture. And I'm kind of using this equality here, even though, what does this picture even mean? But they're the same. They determine one another. Right. So it's going to be important later today that K can be defined over arbitrary weights like 3, 4, 4, 2, 1, arbitrary integers, and we don't have to just take partitions. So keep that in mind as we go forward. Okay, but as I referenced when I first started talking about these Katalans, they were used to define an important family of functions called the closed Kacher-Katalan functions. So this was done again in that first paper by Blasiak, Morse, and Seelinger. They wrote down this definition where they took Katalan functions, and instead of using 3 different parameters to define these guys, they just take a partition lambda, and that's all you need to define this Katalan function. Well, you're maybe saying, how is that all you need when you just said the Katalan is defined on 3 parameters? Well, the way it's done with the closed Kacher-Katalan is that you take your partition lambda, or here I'm using a different one arbitrarily, mu, and you can define delta K of that partition. I'll sometimes call this the Kacher root ideal that comes from our partition. So every single partition has one Kacher root ideal corresponding to it. And we'll plug that in as our parameters. Now you might be saying, sure, that makes sense for the first one, even though it might not be immediately obvious that this is a root ideal. You'd have to kind of like prove that and check it. But how are we allowed to use a root ideal in our second argument when I said this has to be a multiset? Well, the way it works is that if you have ordered pairs in your second argument, you'll simply take the second value of every pair in this set, and that's what you'll use to define your multi-set. You'll kind of forget the first argument of every ordered pair that's in here. So here's an example of something like that. If I were to have L as 5 here, so we have our 5 by 5 grid, but I've taken K to be 4. Again, K and L, they're fixed. We're kind of just leaving those aside. I will take my partition 4, 3, 3, 1, 1. And by the way, I sort of glossed over this detail, but in general, once we have our K and L fixed, and we're defining our Katalans for the closed K-sure guys, I will only look at partitions that are at most L parts, and the largest part of our partition will be K. So I'll call those like K-bounded partitions. So it's important that I've taken 4 as the largest part. I could have taken 2, 3, or 1 as well, but I couldn't have taken like 5, for example. Anyway, just a little detail there. But once I've fixed K and L and I have my partition, this is what the picture would look like for those values. One thing I'll say that turns out to be important about the combinatorics of the closed K-sure Katalan functions is that it's not actually a coincidence here that the red box and the little dots coincide. Like in general, when we're working with a closed K-sure Katalan function, we'll always have that where I have the red boxes or my root ideal, that's exactly where I have my dots or my lowering ideal. Whereas for an arbitrary Katalan function, that definitely doesn't have to be the case. Like the example we were looking at initially, that wasn't the case. That's meaningful because there are quite a few rules in terms of rewriting Katalan functions that rely on where the boxes and dots are. And we'll talk a little bit about some examples of those later today. And so, okay, now that I've given you this definition and I've mentioned that they have this picture corresponding to them, let's start talking about what's known and what we want to know about the closed K-sure Katalan functions. I referenced this kind of when I first mentioned them on the first slide of the talk, but the reason people talk about these functions, or the reason why I started looking at them, is because they were conjectured to have an important relationship with Monk's formula for the quantum growth indique polynomials that Leonard and Mino proved quite some time ago, and I'm going to show you what that is in a moment. But just, holding tight for a second that they're conjectured to have a relationship with the multiplication rule, that might clue you in on the fact that what I do and what others have done with these functions so far is tried to multiply them. And multiplying these guys together and then writing down what that looks like in terms of the closed K-sure Katalans is hard to do in general. We know it can be done because, as I mentioned, they're a basis, but the structure coefficients, they're not obvious at all. But the first sort of non-trivial expansion that was done with them was by Seelinger in his PhD thesis. And here's what he said. He fixed one partition lambda. I'll call that my arbitrary partition. It's like an arbitrary K-bounded partition with at most L parts. It can be anything. And then he took another partition that's pretty strictly defined. So this RD, when you see RD, that is notation for what's called a K rectangle. So a K rectangle, if you fixed K, is when you take some other integer D that's K or smaller, and you write down this partition. So it's just K plus 1 minus D repeated D many times. So we'll see an example of this in a second. But for now, just understand that a K rectangle is very, very narrowly defined. In fact, only K of them exist for some given K, because the other ones kind of don't make sense in a certain way. When you index your closed K-sure Katalans by those partitions, Seelinger showed that the product is extremely beautiful. the product turns out to simply be the closed K-share Katalan indexed by the partition formed by taking lambda, that was our first partition, and RD, our second one, and just sorting the parts of those guys. That's what lambda cup RD means. So here's an example of something like that. Over here, 2, 1, 1, 1 is our arbitrary partition, and 2, 2, 2 is an example of a K rectangle given K equals 4. So you could kind of check that. But when we take those two closed K-share Katalons, this is what the product looks like. I've just taken these two partitions and sorted them. Okay, so that's very exciting. Sometimes that's called the K rectangle property for the closed K-share Katalons. And then what I wanted to do is just up the ante slightly and take like a small perturbation of that sort of idea. And so here's what I mean by that. In Seelinger's work, while we allowed one partition to be arbitrary, our second one is some number repeated several times. What I want to do is take those kinds of partitions, those K rectangles, and simply ask what happens if I take a K rectangle just exactly as defined here, and I just do that exact partition, but the last one, I'm going to decrease it by 1. So for this example, what that means is instead of 2, 2, 2, what if I took 2, 2, 1? And the hope would be that since this is just a rigid change, I'm going to sometimes call rigid changes like that K rectangles minus a box, because that's really all I'm doing. I'm subtracting by 1 or 1 box if we were to draw the, the Farrer's diagram or something. The hope would be that that also has a clean rule that comes out of it. But here's an example of what actually happens. In this case, we actually get 5 K-share Katalan functions, and they don't cancel out. This is the 5 that we get. You can see that some of them have negative coefficients, some of them have positive coefficients, and looking at them sort of right off the bat, there's not like a particularly clean pattern that can exactly emerge based on this information. Now we're going to take something like this and find those clean patterns, but for right now, maybe, the first time ever looking at it, it feels a little bit hopeless because, yeah, it's just not obvious what the relationship between these partitions is to the initial ones that we worked with. So let's start to talk about how we can find, useful patterns out of this data. To do that, to look for those useful patterns, I have to talk a little bit about covers. So covers were, as far as I know, they were introduced, I believe, in 2018 by Blasiak, Morse, Pun, and Summers. And they introduced this machinery in some of their papers about the Katalan functions and K-share functions in order to do something called K-share straightening. And covers kind of have a long definition, but we're going to figure it out together. But before I can get to it, I again have to build a little bit of machinery. So, okay, let's dive into that machinery. The first bit of it is that I'll define a removable root of a root ideal as a root that if we got rid of it, we would still have a root ideal. So again, remember, root ideals come from Dick paths. And if we get rid of one of the boxes, if that box is sort of along the outer edge, maybe we can still have a root ideal. Maybe we can still have something that comes from a Dick path, but there are a lot of roots where if we deleted them, we wouldn't. I'll show you an example of what I mean in a moment, but okay. So there's something called a removable root of psi, and it might have multiple. And then I'm going to define up in psi of x as I if we can remove the root ix. Let's just look at a picture. I think this is going to become way easier. So first of all, let me tell you what a removable root is. in terms of this picture. The red boxes here form a root ideal. Ignore the purple boxes for now. So what we're looking at is just a root ideal in red. Now, if I were to get rid of, let's say, this box here where my mouse is, I'm hoping you can see the mouse so that I don't have to pull out annotation. Okay, great. If we were to get rid of this box, that's still a root ideal. It's a different root ideal, but it's still a root ideal because it's on this like outer perimeter. And moreover, by getting rid of it, we maintain every box to the right of it is still in the root ideal. That's kind of what it means to have this post set that I'm working with. This root as over here, that's also removable. If I got rid of it, we still have a root ideal. This box, no. If I got rid of this box, that's not coming from a dict path because the path would have to sort of snake in this weird way that we don't like. Similarly, we can't get rid of, say, this box over here, like any of the boxes where my mouse is right now, because those are like inside the root ideal. Those are not removable. Okay, so we have this idea of a removable root. And if we start with, let's say, 10, and we go up, the first root that we hit, if we got rid of it, we would still have a root ideal. We would then say that up of 10 in this case is defined. Okay, and we can actually keep playing this game with what we obtain in that way. So in this example, when you go up to 10 and you hit this guy, we would then be, if you move to the left, we would be in the 8th column. Let's try it again. If we're now at 8, and I'm just going to ask the question, does up of 8 exist? The way we answer it is we go upwards until we hit the first root that we can. If we can get rid of it, up exists. If we can't, then it doesn't exist. In this case, again, it does exist. Up of 8 exists because we can get rid of this guy. And I would say that it's 5 because, we move this way and we get to the 5th column. So we can keep playing this game. And if we do this, we form a list of numbers. In this case, it's 10, 8, 5, 2, 1. Just by repeatedly computing up every time that we can, we'll call that an up path. And down paths are defined very similarly. I won't say it explicitly, but it's like the opposite of what I just did, going in the opposite order. Now, the up path for 10 consisted of 5 numbers. If we tried to take the up path of 9, so different example, what I would do is I would start here and I would move upwards just as I did before. And the first root that I hit here is not removable. Therefore, I would say that up of 9 with this root ideal does not exist. And so the up path of 9 would be vacuously defined as 9. So it's not empty. It only consists of the first thing that I was computing. So up paths can be at their shortest, they include 1 number. At their longest, they can be, quite long. I mean, we just keep going until we can't compute anymore. Okay, so that's what an up path is.
May I ask a quick question?
Yeah, definitely.
So the last number in your up path is always something where up of that number is not defined, correct?
Exactly. Yes.
Okay.
Yeah, you have to stop when you can't keep computing up. In this case with 10, we got all the way to the top, so it just so happens that we end with 1, but yes, that's a good point to make. Great. Okay, so that's how we form our up paths. Awesome. Okay, cool. So now that we've defined up paths and the concept of up in general, we can say what a cover is. And I'm going to kind of define it in this like rough and tumble, like algorithmic way that is not shown in the paper, but I feel like it's easier to understand if you're seeing it for the first time. So here's how it works. We'll take lambda k-bounded partition, and to define a cover, we have to fix an integer z that is in the set 1, 2, 3, and so on until L. That's what L with the brackets around it means. Okay, what we'll do is we'll set mu as the partition lambda with 1 subtracted from the zth part of it. That's what minus epsilon of z means. And then I'm going to set psi as the K-Shur root ideal corresponding to mu. Here's how the algorithm is going to work. If Z is L, so it's like kind of the biggest number we could have picked here, or if lambda Z was strictly greater than lambda Z plus 1, then we're done. Cover Z of lambda in that case is just lambda minus epsilon Z. So we don't even really need to work with mu much in that case. Very simple. Okay. Another sort of simple version of cover, so like if that fails, then the next thing we try is we look at the length of the up path of Z in psi and the length of the up path of Z plus 1 in psi. And the length being like the number of elements in the set. So if up path in psi of Z has more elements or the same number of elements as up path in psi of Z plus 1, we're done again immediately. We again have the same exact thing. Cover Z of lambda is lambda minus epsilon Z. So those are kind of like the two easy cases. Sometimes I'm going to call these the H equals 0 cases. And you'll see why maybe in a second. The third possibility, so if both of those have failed, there's only one other thing we can do. We have to define this number H. The way we define it is such that it's a number maximal, wherein mu is constant on a series of intervals. And I know it's pretty ugly, but basically each of the intervals comes from the up path in psi of Z. Until we get to the very top of it. And I haven't defined what y is, but y plus 1 is also coming from the up paths. It's actually coming from the up path of Z plus 1. So it's just some ugly thing that we'll kind of see definitions of in a second, but just take for granted you can compute H in this case. It's just some number. Once you've computed it, cover Z of lambda is a little bit more complex than the previous two instances. It's going to be lambda with 1 added. So the other ones we're not adding 1 in any parts. These other two, we were just subtracting 1 in the zth part. But for this third case, we do add 1 to lambda in certain parts. It's in H parts of them. It's in part y plus 1, part y plus 2, and so on until part y plus H. Then we subtract in H plus 1 parts, okay? So the parts that we subtract from are Z, Z plus 1, Z plus 2, and so on until Z plus H. So what you'll notice in all three of these outcomes is that we always subtract in exactly 1 more part than we add. Now it was simple here because we only subtract in 1 part and we add in 0, but this parity of like where we add and where we subtract, it's preserved in this last version as well. Okay, so let's do examples so that this becomes a little bit easier. And I'll tell you why that parity that I was talking about matters a little bit later. So if we were to take 3, 3, 3, 2, 1, 1 as our partition, and we take k equals 4. I've drawn the K-Shur root ideal, but you don't even need to worry about the black dots or anything. Just know that this is the K-Shur root ideal, and remember the K-Shur root ideal is essential to defining a cover. What happens is that cover 2 of lambda in this case is 4, 2, 2, 2, 1, 1, and it's a partition. To show you how it works, like unpeeling what I had on the previous slide, is that the way I computed cover 2 is I go to 2, the second spot. Remember, this Z is just telling you the number of the part, not what's in the box. We go to the second part and we look at the length of its up path. In this case, the up path is length 1. It ends, right? Okay. But what about the next guy? Well, the up path is longer. It starts here and then it goes up here. That means that we're in the third case. The third case of cover tells us to compute y plus 1 and so forth. And in this case, this is what you get. Cover 3 is a little bit simpler. The third part is strictly greater than the second part. And cover 4 is also kind of simple. Cover 5 is maybe an interesting example. Cover 5 if you were to chase that definition from the previous slide, you would see that it is not a partition. So covers do not have to be partitions. We can always compute them, but they're not always going to be partitions. Okay, fine. That's not a big deal. Next kind of interesting thing you might notice about covers is once you compute a cover, you get a partition. So you can just compute another cover of it if you want, right? Now, theoretically, you couldn't always do that here. Like this is not a partition, cover 5 is not. So maybe computing a cover on that one doesn't make sense. But cover 4 was a partition, so we can immediately apply the definition to it. Now, and take cover 2 of what we got. Now, in this case, cover 2 of cover 4, I would call that a chain of covers. It just so happens that that's the same thing as starting with taking cover 2 and then computing cover 4 of that. Like you could say that the chain commutes maybe in this case. That's not always true. That's a coincidence. And that turns out to be really, really, really important when it comes to the combinatorics of Katalan functions that I'm going to talk to you about more in a second. But sometimes they commute, sometimes they don't. This sort of matters. Okay, so covers, there's some operation that you can do on partitions. The reason why I showed you covers and made you like sit through that definition is that they're super important for working on examples like the one that we were just looking at a few slides ago. So this is just that same example we were playing with. And it just so happens that in this case, what's lurking beneath the surface is covers and chains of covers. So the top line corresponds here to taking cover 4 of lambda cup RD. So this is not the rectangle minus a box, even though that's what I'm starting with here. And then the second function came from cover 6 of that same partition. The third one came from cover 7 of that. Okay, so those were sort of our positive terms. And then the second line came from chains of covers, like length 2 chains. So I started with cover 7 in both instances, then I computed cover 6, then I computed cover 4 over here. So, you know, how did we see that? How on earth did we know that that was lurking under the surface there? Well, of course, it's not immediately obvious. I mean, for one thing, why am I using 4, 6, and 7 as our index set? Why don't I use 1, 2, 3, or 5 as where we compute covers on? Moreover, I took covers here of 4, 7, and 6, 7, but why didn't I do something like 6, 4? Why didn't I mean, you know, those are two different Z values. Why didn't I take those? That's really not obvious at all. And that's sort of like the crux of understanding this problem. Another thing I'm going to say is that one thing that is a little easier to show than what I was just referring to is that the signs here, that's not a coincidence at all. In general, what we can show is that if we're taking an odd number of covers total, then the sign will be positive. If we're going to take an even number of covers total, then the sign will be negative. So that's very helpful because it predicts the sign in like in a convenient way. But let me show you how we even start to peel through getting 4, 6, and 7 as what the covers index. And let me check how I'm doing on time. Okay, 9 minutes. Cool. Okay, so here's the first non-trivial thing that I showed to help us with this problem. So RD star, by the way, that's just notation for a rectangle minus a box. So the first thing that I saw was that this product expands into a sum of Katalan functions that is determined by a certain set of down paths. I'm not really going to explain how I calculate D and R and so on, but these are like determined by lambda and RD. I mean capital D. But anyway, the point is the first thing I was able to show, and this was very similar to the way Seelinger approached his K-rectangle rule, is that I can write down this product in terms of Katalan functions. Unfortunately, that doesn't get us too far because we don't care about arbitrary Katalans. We want closed K-sure Katalans. But here's how something like this would play out. So I know I said that I'm not going to define capital D and R and so on, but here's how this proposition would work with an example. If I were to take the Katalans that I've been using as like my running example, what I would do is take the numbers 4, 5, 6, and 7. That's like what's obtained by this R and D and all of that. And the first like line you can think of is just the Katalans indexed by 1 descent, each of those. Then we'll take negative signed Katalans where it's every subset of size 2 of 4, 5, 6, and 7. So this is huge. I mean, we'll start with maybe 4, 5, then we'll do 4, 6, then we have 4, 7, then we do 5, 6. It's long. I couldn't fit it all on this slide. And we keep on taking subsets of 4, 5, 6, 7 until we get to the last term. In this case, it's just, the whole set itself, 4, 5, 6, 7. Okay, so we have this like long thing of Katalans. How on earth can this take us closer to the idea of covers? Well, the next non-trivial thing that we might notice is that taking Z, a subset of size 1, so it's just one element, as before, it comes from this capital D that I didn't go completely into detail about. What we can show is that this Katalan function, which is the type that was formed by the rule on the previous slide, is actually just the Katalan function defined using covers and the K-sure root ideal corresponding to it. So example here is that with this function from the previous slide, this can be rewritten as K delta 4 of cover 4 of lambda and so on. Now again, remember, cover 4 of lambda or any cover of lambda does not have to be a partition, but it can be. And if it is a partition, this is exactly the definition of a closed K-sure Katalan function. I'm not doing anything special. This is just literally what the definition says, is that a closed K-sure Katalan is just one partition here, and then the K-sure root ideal of it, and then the K-sure root ideal of it as well. Okay, so cool. Like a corollary to this proposition would be that if cover Z is in par, then cool, we get back the closed K-sure Katalan function. Now, this feels a little promising because what we can do is go back to an expansion like this and rewrite all of these, at least for the first line, as things that are pretty darn similar or exactly the same in some cases as the closed K-sure Katalan. The problem is when it comes to terms like this one where my mouse is. In this case, like with these specific numbers, cover 5 of this partition is not, it's not in par. It's not a partition. And so we don't want terms like that. They're meaningless from the perspective of closed K-sure Katalan functions. What would be so awesome is if we could show that in that case, what we get from this proposition is identically 0. It would mean that those sort of just vanish. They're gone and we can eradicate them from the sum. It would be awesome, but that's false. That's not true. That's absolutely not true, but it does turn out that those are the functions we want to get rid of. So we'll have to approach this from a cancellation perspective so that we can collect these useless terms and show that when put together, they become 0, but on their own, they are not identically 0. Okay, and so one other thing I'll note is that this proposition was like a baby step. We only took cover Z, but as I said before, you can take chains of covers. You can compute cover after cover after cover. The problem with that in this regard, or maybe just in general, is that as I said earlier, order matters usually when you're computing covers. You can't just, compute in some order and expect to get the same thing as computing in some different order. Moreover, the way I'd like to order these based on some extra information that I have is not necessarily in increasing order. So what I mean is, like, when I take 4 and 6, I don't necessarily want to compute cover 6 first and then cover 4 afterwards. I actually don't always want to do that, even though sometimes I do. So the question becomes, what is the order that I want to move in? And so that order comes from some other stuff that was mentioned in the title, which I think was covers and chains. So there are other things that we can take chains of besides covers, and that's what I'll maybe talk about in 2 minutes. So in order to talk about where that ordering is going to come from, I have to go back to why the closed cache or Katalans matter at all. So these guys matter, as I said before, because of something called Monk's rule for quantum growth in Dieck polynomials that was shown by Leonard and Minot. So this rule, as you'll notice, is not actually defined over partitions. W and SK, these are permutations. So what is this pi that we use in Monk's rule to order W and SK? Because pi is actually going to be chains of permutations. And what I want to do with my partition language is somehow compute covers in an order that exactly matches the language of those chains of permutations. And so what I have to do there is move to that world briefly. And briefly, because I'm not going to go into detail here, but due to my advisor Morse, this is all kind of joint work with my PhD advisor Jennifer Morse. There's a lot of structure that exists that we can figure out with these permutations. The first thing that we'd have to do is note the bijection between the affine Grassmannian permutations and partitions. I'm not going to have time to talk about what I mean by that. It's not exactly the affine permutation group, because I'm letting or the affine Grassmannians, because I'm letting R be non-zero. If you let R be 0, that's exactly what that is, but this is like the extended analog of it. But anyway, there's a bijection here between these guys. And so what I want to do to take it all home is to look at chains of covers like that in the right-hand world over here, and then look at the ordering that exists in this affine Grassmannian world, where I start with a permutation, and then I draw an arrow by applying some tau AB, and then I maybe apply some other tau CD, and so on. And I want to show that these types of chains exactly coincide. And by doing that, I can say the order that we need to move in when we compute covers. Okay, and that's all I wanted to say. So thank you so much. I will maybe stop to take a few questions if anyone has any, because it's 10:51.
Yeah, great talk. Any questions?
So what goes into your proofs?
Sure, yeah, that's a good question, since I didn't say anything about that. A big part of the proofs about the expansion as covers really comes from combinatorics of root ideals. So, I was saying that these are important, but I didn't go into why pictures like this matter. But basically, before showing the bigger kinds of proofs, we need to work on a very granular nanoscale with root ideals, and show things like what happens if you have a picture like this, but there's only one more dot here than there is in this column. Another example of the kind of thing we could look at is what happens if you have a grid like this with the same number of roots here, but this part is, let's say, exactly 1 less than this part. So imagine like we have 0, 1 here instead of 1, 1. Then also things like root expansions, which Blasiak, Morse, and Seelinger did a lot in their paper, turns out to be very useful for work like this. A root expansion is when you take a Katalan picture and then you remove just like 1 box, 1 root, and then you say, what does that look like as a sum of Katalans? So like in general, you can write this picture as this picture without this box plus some other stuff. That kind of stuff is very useful. So I work in like a very, very, very combinatorial world with root ideals most of the time.
Oh, cool. Thank you.
Yeah, sure. Thanks for the question. Yeah, thanks. I don't know if there are any other questions, or maybe we're good.
I think we're good. Let's give Mojda another round of applause.
Thank you.
Thanks. Yeah, thanks.